So again, I'd like to welcome you to today's MSDN webcast. This is Planning for Enterprise Scalability and Performance with SQL Server 2005 Analysis Services. It's my pleasure to introduce today's presenters. We have TK Anand. He's a program manager at Microsoft, as well as Christian Peklueska, who is an architect with Microsoft. So gentlemen, I'm going to hand it on over to you and let you take the floor.
Thank you, Janet. Hi, my name is TK Anand, and as Janet said, I'm a program manager in the Analysis Services team, and I have Christian, who is an architect in our team. And we're going to be talking to you about designing for performance and scalability with Analysis Services. So just so that we have the expectations set right, here are the objectives for the session. So we're going to be focusing on designing cubes for performance and scalability, best practices for cube design, understanding performance implications with dimension and cube design, that sort of thing. We're not going to be covering a whole lot of details on dimensional modeling and advanced analytics. We're not here to compare performance with Analysis Services 2000 or provide any kind of feature overview. So it's specifically focused around best practices to attain the best possible performance you can out of your cubes. So with that, let's get started. So here's the high-level agenda. We do have a lot of content here. I've tried to reduce the slides to a minimum to fit within the hour, but we will be going pretty fast. I have Christian with me, so he will be answering questions along the side, and at some point I'll swap with Christian, and he will be doing the slides, and I'll be answering your questions. So let's start with the first section on server architecture, and let's get going. So on the right, you've got the analysis server and client applications that communicate with the analysis server. By client applications, I mean both end-user-oriented applications like Excel, as well as administrative applications like the BI Development Studio, SQL Server Management Studio, and Profiler. All of these applications communicate with analysis services via the XML for Analysis protocol. XMLA is an industry standard that Microsoft has extended in SQL Server 2005. So Analysis Services now uses XMLA as the backbone for all of our client-server communication. Now at the transport level, we offer both TCP as well as HTTP connectivity, but the bits that flow along the wire are still XMLA. Now, the client applications will typically communicate with Analysis Services using one or more of our client APIs. Probably the one that's been around for the longest time is OLADB and OLADB extensions for OLAP and data mining. So Analysis Services has an OLADB provider for SQL Server 2005, and certain client applications like Excel make use of this OLADB provider. Now, the Microsoft Data Access Components, which ships as part of the Windows operating system, has a component called ADO-MD, which is an OLE automation wrapper on top of OLADB. So VB6 applications usually take advantage of ADO-MD. VB-script and JavaScript applications can also take advantage of it. We also have a .NET equivalent for ADO-MD known as ADO-MD.NET. So if you're building .NET applications, this is the preferred way to go. And we also have an administrative object model called AMO, which is the replacement for DSO, if you're aware of that from the SQL Server 2000 days. But the bottom line I want to make is, in terms of this client-server architecture diagram, is we have a rich set of client object models and APIs, but all of these object models essentially wrap the XMLA protocol. They're all thin clients that send XMLA requests to the server and parse the XMLA responses back and expose it to the client application via an object model or an API. Unlike Analysis Services 2000, none of these object models do any heavy lifting in terms of caching or query processing. So let's take a look at the same picture from a middle tier perspective. Again, it's nothing very different from what you might know with Analysis Services 2000, but the main thing to note is that now these client APIs or object models living on the web server tier, since they are lightweight XMLA wrappers, the middle tier becomes a lot more scalable. So APIs like OLEDB and ADUMD.NET have a much smaller memory footprint, and even in terms of CPU utilization, they are pretty lightweight. So the web service tier can scale a lot more in SQL Server 2005. So just to summarize, the thin client architecture, the client components are lightweight XML wrappers. They do not have any client-side logic for query processing, no intensive data caching like we used to do in Analysis Services 2000. Of course, this approach has pros and cons, but in general, we decided to go with this approach because, first of all, this results in all of the processing being done centrally on the server, better utilization of server resources. It is less demanding on the client machine in terms of memory and CPU. Of course, there are certain cons associated with it. Now, queries all have to make a round trip to the server. So if there was any possibility of client-side caching, that would it would not take any advantage of that. So in general, the thin client architecture offers a lot of benefits, but just know that there are certain negative implications of it as well, and we just believe that the pros and cons, in general, the pros outweigh the cons in the long term. Okay, so with that, I'm just going to go over to the next section on UDM basics. Now, this is an advanced talk in terms of performance and scalability, so I do assume that the audience is relatively familiar with the Analysis Services 2005 product and the tools. I'll just use this section as a quick kind of a primer on the UDM, so we're all on the same page. So the dimension model, the dimension model is where a lot of the major changes have occurred in Analysis Services in the last release. So it's worth spending a few minutes on that. So fundamentally, dimensions now consists of attributes. Now, in this example, you've got a customer dimension with a bunch of attributes like country, state, city, and gender, and so forth. And these attributes have relationships between them. Now, based on these attributes, you can create multiple hierarchies. So in this example, I've got 3 different hierarchies that have been created in this dimension based on the set of attributes. Now, attributes also automatically come up with what are called attribute hierarchies. Attribute hierarchies are these single-level hierarchies which expose the dimensional space in sort of a normalized manner. So this is the overall dimensional model, as you should be aware of if you've played with the product. So you've got attributes and a bunch of user hierarchies and attribute hierarchies that constitute the dimensional model. And cubes now consist of multiple measure groups or fact tables. So a single cube in this example can contain a fact table or a measure group for sales, one for inventory, and one for finance. And a cube consists of a bunch of dimensions. Now, the multidimensional space of the cube is composed of all of these dimensions and all of these measure groups, but not every measure group consists of every single dimension. For example, sales is dimensioned by customers and products, but not, in this example, department and account. Similarly, the inventory measure group has no relation to the customer dimension. So this matrix representation kind of gives you the high-level picture as to what measure groups or fact tables are associated with what dimensions. So that kind of gives you a high-level picture of the dimensional model and the cube model. It's a very quick baseline to make sure that we're all aware of what I'm going to be talking about in the future slides. Okay, so let's move on to the next few sections, which are the crux of the talk. So I'll first start by spending a bunch of time on the core cube design and best practices for the cube design, and then Christian will take over to talk about partitioning and aggregations and the other sections. Okay, so let's get going. So first of all, for good cube design, I always put up this slide at the beginning. There are really 3 core things that you need to know, and once you're aware of that, I believe that you will go a long way in optimizing all of your cubes. So the first one is attribute relationships. The sooner you get to understand attribute relationships and are aware of that in your dimensional modeling, the better off you are. And the second tenet is, well, attribute relationships. And the third one is, again, attribute relationships, as you've got it. So I can't really emphasize this enough. Unfortunately, our product and tools have not done the best job of surfacing attribute relationships very clearly and upfront in the user interface, but just know that you have to pay a lot of attention to detail with regard to attribute relationships if you're producing any cube of a medium to large scale and you're really interested in extracting the best possible performance out of it. For small cubes, proof of concepts, that sort of thing, you might get away with not worrying about attribute relationships and be fine. But when you're really getting into seriously large-sized cubes, you need to start paying attention to this. So a lot of this section is going to be spending time on talking about attribute relationships. Okay, so what are these attribute relationships? You already know what are attributes in a dimension. So attribute relationships are just one-to-many relationships between the attributes. Now, certain relationships are automatically defined in the dimension when you create it, but certain relationships have to be specified. And the bottom line is the server just works better when you define them. So examples of these are city to state. So you know that every city lies in a state and every state lies in a country. So those are just natural relationships between these attributes. And I have other examples for days and months and quarters and product categories and subcategories. All of these are natural relationships between attributes that exist in your dimensional data. But the analysis server and the cube designer doesn't know necessarily about all of these relationships. Pretty much the only relationship that is implied automatically is the relationship to the key of the dimension. Every dimension in analysis services has a key attribute. So for example, in a customer dimension, the customer IDs or the individual customers form the key of that dimension. For a product dimension, it's the individual products. Now all other attributes in the dimension have an implicit relationship to the key. But that unfortunately is not sufficient. You should be spending time specifying these richer relationships such as city to state and state to country if you want to get the best possible performance and functionality out of your cube. So that's what the last bullet point is saying, that all attributes are implicitly related to the key. Now these relationships can be rigid as well as flexible. So rigid relationships are by their nature relationships that don't change. For example, the birth date of a customer is typically not going to change. City is not going to move from one state to another, so that's again a rigid relationship. But typically other relationships, like a customer's address or the city where he lives in, is subject to change, so those are flexible. Now all relationships by default are flexible, so the server assumes that they're going to change, but you're better off marking specific relationships as rigid if you know that they are in fact rigid. So here is an illustration of these attribute relationships. I've already shown it to you in an earlier slide. You've got the default relationships from gender and marital status and city going to the key attribute, which is the customer. But then you've got these additional relationships like city to state and state to country, which are things that you would have to explicitly specify when you're modeling your cube. Okay, so why are these attribute relationships so important? Where are they used? Well, this is a talk about performance and scalability, but it's worth mentioning that attribute relationships have application in just more than just performance. So for example, MDX semantics. Attribute relationships tell the MDX formula engine how to aggregate measure values. Typically, a lot of cubes have data at the granularity of the key attributes. And in that case, you might never actually encounter this problem. But let's say, and this is not very uncommon, let's say you have a sales measure group where the sales are at the granularity of individual months and not days. Now the formula engine has to say, okay, I've got some sales by month. How does this data roll up from months to quarters and quarters to years? Well, if there is no relationship between months and quarters, the server is not going to roll up any data to quarters and years. So you need those relationships there. Otherwise, you would just get nulls. And the second point is just talking about positioning with respect to calculations. But the essential gist of it is that without good relationships, the semantics of your queries are going to be not what you intended. Okay. What about storage? Now, specifying good and normalized relationships is also going to be optimizing the dimensional storage. It's going to be helpful in clustering records within the partition data. Processing of dimensions and partitions are going to benefit from normalized attribute relationships, especially when you're talking about large dimensions. The better the attribute relationships you specify and normalize, your dimensions are going to be able to process faster and consume less memory. So all of these are benefits. Query performance I've already talked about a little bit, but the fact that normalized attribute relationships reduce the dimension storage, well, then there's less data to scan. As a result, the query performance is going to benefit. The execution plans chosen by the formula engine are going to benefit. We're going to spend some more time later on aggregation design, but just to state it at a high level, the aggregation design algorithm heavily depends on attribute relationships to choose the right set of aggregations. And finally, attribute relationships are also member properties. So if you're used to member properties from the Analysis Services 2000 product, specifying an attribute relationship also gets you a member property, but you can set a visible flag to true or false if you want to turn it off. Okay, so at this point, I just want to show you a quick demo on how to actually set up the attribute relationships and what are some of the gotchas and problems that you should be aware of. So I'm going to switch to application sharing at this point, and let me open up my demo folder, and I'm going to open up this solution. It's just a simplified solution based on the AdventureWorks database, and it's just got a single cube and 3 dimensions: product, customer, and date. So I've got the date dimension opened up here, and I'm going to this cube is processed, I believe. So let's just quickly browse what the date dimension looks like. I've got a hierarchy called year, quarter, month, and date, and I open it up. Okay, you've got 4 years. Open up this year. This dimension actually looks fine. You've got quarters, months, and days. But let's go look at the dimension structure. Now, in Service Pack 2 of SQL Server 2005, because of customer feedback, we've actually added these warning signs to explain the lack of attribute relationships. So, for example, you see this warning sign here on this hierarchy, and if you hover over it, it talks about missing attribute relationships. Basically, the fact is that when I open these up, you'll see there are no attribute relationships defined. So although your hierarchy is going to look fine, it's not going to perform the best. So let's go fix that. So firstly, I need an attribute relationship from year to quarter, because we know that quarter to year is an inherent relationship. Similarly, from quarter to month, that's a relationship that you typically want. And then from month to day of the month. Okay, so these are all good attribute relationships, and now you see that the warning sign has disappeared for this hierarchy. Now let's go ahead and deploy this, and so there we go. So I'm going to just quickly deploy this project and just see what my hierarchy looks like. So once I've fixed these attribute relationships, I expect to see a hierarchy that looks the same, but the performance of browsing the hierarchy and browsing cubes that depend on this hierarchy is going to be better. Obviously, in this demo, I'm not actually going to prove to you that the performance is better. You'll have to take my word for it. Let's reconnect and see what's going on. Oh, okay, so there's a problem here. The year 2001 doesn't have any months in it. 2002 has 1 quarter, quarter 3. 2003 has quarter 4, and quarter 1 and 2 have shown up under 2004. Well, what is the problem here? The problem here is that just specifying attribute relationships is typically not enough. Analysis Services requires that you specify unique keys for all attributes. Now, the key of an attribute is what is specifying the distinct members of that attribute. So an attribute relationship, remember, it is a one-to-many relationship. So you must have a one-to-many relationship between the key columns of these 2 attributes that you're specifying a relationship for. So in this case, what's happening is that The quarter, let's go back to the browser. Quarter has 4 possible values, 1, 2, 3, and 4. But guess what? There is a quarter in every year. So analysis services thinks that there's only 4 quarters, so it decides to stick those quarters in arbitrary years during the dimension processing. So the solution for this is actually to specify unique keys for the attributes. Remember, analysis services always requires unique keys, and the way you can do that is by using composite keys. So let's go ahead and do that. So for the quarter attribute, I'm going to click on quarter, come down here, and here's my key column. See, the key column just says calendar quarter. So what I'm going to do is, in addition to calendar quarter, I need to qualify this key column with the year as well. So I'm going to say add, specify a source, specify column binding, and pick the calendar year. So now my key column is a combination of year and quarter, and that is a qualified name. Now let's go and do the same for month. Again, I'm going to add a new key column, add the calendar year, say OK. And finally, for day of month is actually needs 3 key columns to qualify it. So it's not just the month of it's not just the day of the month. I need the calendar year, and I also need the month of the year. Okay. So once I do this, actually now I get a little squiggly under day of month because day of month did not have a name column specified. So I will need to explicitly specify it because I have a composite key column. So I'm going to just take the month, the day of the month. So I need day number of month. Okay, so I've got that. And my squiggly has gone. Let me go ahead and just F5, deploy this project and see what happens. So you see that attribute relationships, although they're very important, you need to pay specific attention to the key columns as well. Analysis services assumes that all attributes have unique key columns specified. If you're used to Analysis Services 2000, things were a little easier. You could use this property called member names or member keys unique to get away with it, but in 2005 you need to be a little more careful about it. So let me refresh again, and voila, my hierarchy now looks much better. It is back to the state it was when we started the demo, only now I have the attribute relationship specified, and it's going to perform a whole lot better. Okay, so let's go back to the slides. Okay, so I just have a couple of slides just summarizing what I went through in the demo, so I'm not going to spend too much time on it. So the bottom line is, it's not enough to just create attribute relationships. You have to make sure that the key columns are right. You can use composite keys to make the key columns unique. You can also do other tricks in the data source view to produce unique key columns. I suggest you look at the AdventureWorks sample database. It has a lot of interesting ideas on how you can produce unique keys and use them in your attributes. Like we've seen, if you specify invalid or non-unique key columns, your hierarchy will end up looking wrong because the dimension processing is going to pick parents that are arbitrary, and the resulting hierarchy is not going to be what you want. And here is an example in a slide, but it just describes what we have done. You can use composite keys to specify the unique key columns. Now, one thing which I actually didn't do in my demo is this, which is after you've correctly added your attribute relationships, you should also be removing the redundant relationships. So, for example, if you've got a relationship from city to state and state to country, well, you don't need a relationship from city to country. Any relationship that can be inferred through other relationships is redundant, and for performance reasons, you should be removing those. So I have examples here. For example, customer to city is obviously not redundant, but customer to state can be inferred, so it is redundant. So it's strongly recommended to go through your relationships and delete these redundant relationships. Now let's switch from attributes to hierarchies. User-defined hierarchies, what are these? Now, user hierarchies are basically predefined navigation paths that use the attributes to construct navigation path through the dimensional space. Now, you can always navigate through the dimensional space using attribute hierarchies, but what user-defined hierarchies gives you is, first of all, Your end users have predefined navigation paths to use. A lot of client applications that are built for Analysis Services 2000 are not attribute aware, so to speak. So having user-defined hierarchies definitely helps there. And the bottom line is that once you've defined user-defined hierarchies, Analysis Services optimizes for them at processing time. So for example, it will create the tree that represents the hierarchy and materialize them on disk at processing time so that you don't incur that performance at query time. So the bottom line is user-defined hierarchies are a good thing. So just because Analysis Services has moved to an attribute-centric model does not mean that you stop creating user-defined hierarchies and let your users do ad hoc navigation. Ad hoc navigation has its place, but user-defined hierarchies are important as well. Now, in a user-defined hierarchy, you have natural and unnatural hierarchies. A natural hierarchy is one in which all of the levels have appropriate attribute relationships defined, like what we did in the demo. So for example, country, state, city, and customer is a natural hierarchy, assuming you've specified the right attribute relationships. If you did not specify the right attribute relationships, this hierarchy would technically be unnatural. So a hierarchy like, if you look at the fourth example, age, gender, customer. Now this is kind of an interesting navigation path, but it's perfectly valid. Now this is a hierarchy that is inherently not natural. Okay. Now why is natural versus unnatural interesting? Well, it's from a performance standpoint. Natural hierarchies are going to be materialized on disk, whereas unnatural hierarchies are sort of like ad hoc navigation. So they are composed on the fly at query time. So you're going to be definitely better off with natural hierarchies. In certain cases, unnatural hierarchies are needed because that's what your users want, and in that case, it's okay. So the bottom line is try to create natural hierarchies by specifying attribute relationships wherever possible. I think we're running a little bit behind time, so I'm going to skip this demo. So let's go back to the slides. So I'm going to finish up this section by outlining some best practices for cube design. So first of all, regarding dimensions, one of the core tenets of the new dimensional model is the fact that you have attributes and multiple hierarchies. So you're highly encouraged to make use of this. So you should be moving away from the Analysis Services 2000 model of creating separate dimensions and virtual dimensions. In fact, virtual dimensions are no more in the new product. So you should be creating multiple hierarchies. Roll-up dimensions are kind of they have their place for very large dimensions, but in general, if you can avoid roll-ups, that's always good because our molap structures are far more optimized than relational structures for high-performance queries. We've got a bunch of interesting features in 2005 which all contribute to better performance. For example, role-playing dimensions. In 2000, you would create multiple physical dimensions to achieve what you could using role-playing dimensions, so you should be using this. Parent-child dimensions are interesting. They provide a very interesting piece of functionality, but again, they do not have the rich aggregation support that other dimensions do have, so you should be using them prudently. If you have a choice between parent-child and non-parent-child, definitely non-parent-child is better. But if you have to, then keep your parent-child dimensions to a minimum. Reference dimensions are an interesting feature. I don't have the time to go through them in detail, but definitely remember to set the materialized flag to true. This basically lets you give reference dimensions the same kind of performance as regular dimensions. Many-to-many dimensions, again, they are. This is new functionality in 2005. We didn't have it in 2000. The only alternative would have been to replicate their functionality using calculations, which is exceedingly slow. So many dimensions are a great benefit, but again, they are not going to be as performant as regular dimensions, so just know that. Okay, moving on to attributes. We've already talked about some of this stuff, defining attribute relationships, removing the redundant relationships. Regarding key columns, it's always a good idea to use compact keys. So using strings as key columns is generally a bad idea. You can optimize your dimensions by setting attribute hierarchy enabled flags to false for attributes that you don't care for navigation. There are other flags that I talk about here in the slides for reference, and you should pay attention to these as well. Finally, regarding measures, again, use the smallest data type possible to represent your measure and the aggregate values for the measure. We've added semi-additive aggregate functions in 2005, and so definitely you're encouraged to use those because they're going to definitely get you a much better performance than if you simulate these behaviors using calculations. Distinct count measures, this is pretty well-known best practice. You should be putting them into a separate measure group. Our UI actually does this for you automatically. And finally, we do allow string source columns for distinct count measures, but strings are generally a bad idea if you can avoid them, specifically for things like measures and key columns. Okay, so I'm done with that. At this point, I'm going to hand it over to Christian to cover the remaining sections, and I'll be taking your questions on the other computer.
Thank you, TK. So TK has given us great advice on how to optimize the cube design. And what I'm going to dive in is how to get even more performance tips and tricks by first looking into partitioning techniques. So first, let's look at what partitioning is. Partitioning is a mechanism that allows us to distribute the data onto multiple physical locations. And the server does not do this automatically. Instead, it empowers the DBA such that he or she can specify what is the partitioning distribution, how data is to be distributed upon multiple physical locations. Typically, data is distributed by time. For example, you might distribute one partition for every month, or by geographic location. And the DBA, as I said, would specify how data in his or her measure groups are to be partitioned. Dimensions cannot be partitioned. Now, why do we do partitioning? Let's look at the benefits of partitioning. Well, primarily, partitioning is done such that data be able to be managed independently. For example, when we want to maintain a sliding window type of data, for example, 2 years worth of data partitioned by month, I don't need to reprocess every month when I add a new month and drop the 2 years ago month. I don't need to process the whole amount of 2 years worth of data. But instead, if I have the data partitioned by month, I add one partition and delete one partition at the end of the month, which means that I just touch 1 month's worth of data each month, which is great processing improvement. Another important benefit is that partitions could have different storage settings, depends on how hot the data would be. For example, and I will refer a little bit later that newest data would be MOLAP and coldest data, so old data, which is much rarely referred to, could be rollup. They could have also different disk drives for maximizing parallelism on disk controllers. So all these great benefits. In addition, they do improve scalability by allowing queries to be physically distributed just to the portions of data that is known to have data for that particular query. For example, if we query data for year 2006, the partitioning technique, if we partition by month, let's say by anyway timely based partitioning, would allow querying only the 2006 partitions, and for example 2005 partitions won't even be touched. In some sense, it's like a clustered index based on the slices of data it specifies. Partitions also improve performance by querying and processing them in parallel, so you can utilize much better your memory and disk resources. So the bottom line is that partitioning allows you to better utilize the machine for greater performance and scalability, and not lastly to optimize to better manage your server. So what are the key points? How can we improve the scalability and performance by utilizing partitioning? First, don't create too big partitions. The rule of thumb would be no more than 20 or so million rows per partition. It's not a hard number, it's more like a guideline. Another advice would be to create what we call heterogeneous partitioning technique, which means partitions would have different storage settings depending on how often you access the data. You would imagine that MOLA partitions with lots of aggregation would be used for latest data, for example, last month's worth of data and previous month, which are used typically by people to browse the data, should be MOLA with lots of aggregation to deliver the fastest query time. The periodically queried could be MOLA, but with less or no aggregation, and all those data could be roll-up such that we save on storage space. Alternate disk drive, if we distribute the partitions across multiple disks, would utilize all the controllers on the machines to avoid the contentions on I/O. And remote partitions, it's an interesting feature. It should be used with care. It's designed to scale out. However, it has its own performance penalty. It improves the scalability, however, at a cost, and the cost is performance. Now that we looked at partitioning, the next performance gain that we can get is by utilizing aggregation. So what is an aggregation? If for those of you who are familiarized more with relational databases, an aggregation is like a materialized view. It's a pre-computed result, a pre-computed group by aggregation. And in the example that you see on the slide, the fact table would have customer ID by SKU. That is the fact table. It contains maybe 1 billion rows of all products sold to all customers. An aggregation, one would say, it would be a group by all customer, all products, which would mean the general total for the units sold and the sales. When would this be used? It's obvious. In case it's not obvious, such an aggregation could be used to answer queries, show me the total for all customers, all products. Well, in this case, instead of summing this up from the fact table at the runtime of the query, we would utilize this aggregation to just read the pre-stored redundant result. And obviously, we can have aggregation somewhere in between, like by country, by item, in which case, if a query comes to country and item, we would utilize this aggregation. So the benefit seems to be clear. Now, how big is an aggregation? Because this seems to be an important point. The aggregations vary. The aggregation size varies depending on how deep is within the granularity of the dimension. Aggregations like all customers by all product by all time are very small. They have only one possible row because of the product of all the product of all the cardinalities of the attributes involved. Well, the deeper you go, the larger the theoretical space of the aggregation becomes. Now, the estimate of the aggregation size is not so simple just by multiplying the cardinalities of the attributes, because data sparsity is involved. As analysis services does not store null data, then the estimate should be factored by data sparsity. So the actual size of the aggregation is reported by a schema row set that we expose in the product. Now, why do we design? We said why we design aggregations, mainly to help query performance. And how do we establish what the performance gain is? Well, typically by how many cells do we need to scan. For example, a query that would come at all in the picture above could utilize the aggregation all, and therefore it would scan one cell. If the query would come to country, item, and quarter, it could scan about 270,000 rows. However, it saves a lot on not scanning the facts, which could be in billions. Therefore, this aggregation is very beneficial. More than that, an aggregation that comes to country, brand, and quarter could utilize even though it was not an exact match, could utilize the right below aggregation country, item, and quarter, which would save, again, scanning the fact table. If an aggregation is not found, then yes, we need to go to the fact table, which results in a performance penalty. So then somebody might say, well, if we want to design for performance, let's put all of the aggregations possible in. Well, that's not so simple after all, because the total number of possible aggregations could be very large. In the example that I considered, the number of possible aggregations was fairly limited, about 125 or so. However, in larger cubes, this number could go to billions, which obviously would explode in terms of the necessary storage. So how do we know which aggregations should we design? Well, there is an aggregation design algorithm which allows us, based on a lot of settings that the user can specify on what the aggregation usage property on an attribute would be, that would allow the system to design the optimal aggregations for querying. The aggregation design algorithm works in what we call waves. It starts from the top of the hierarchies and devolves down to the lower granularities to find the optimum aggregations that are needed for a given storage requirement. So you should use the storage design wizard to maximize your performance by specifying your disk, how much disk you are willing to spend on getting more and more aggregation performance. And how do we know once we design the aggregations if they are good or bad? You could use Profiler in order to monitor how the aggregations are used. For example, we would send a query, which could be an interesting query for us, an MDX query, and then monitoring the event get data from aggregation, we could see when aggregation is hit. And this, in the example that I have on my slide, in this case, this registers a hit, which after that, the progress report begin and end event would show reading the data from aggregation, returning the data cache to the formula engine, and continuing with the execution. If though the get data from aggregation event is not registered, it means we encountered a miss. It means this aggregation has not been designed, an aggregation that would cover for this query has not been designed, so we can even take action. We can design our own aggregation for it. What are the best practices for aggregations? Well, first of all, as TK said, define all possible attribute relationships. Aggregation design algorithms heavily depends upon the relationship you define within your attribute sets. Use the aggregation usage options that are in the cube attributes, such that aggregation designer consider just the attributes you are interested in. And again, as a rule of thumb, I would give you that the number of total aggregations should be in the hundreds and not thousands. And actually, as I'm at it, I can tell you that adding more and more aggregation at some point would hurt performance. Not only performance of processing, which obviously the more aggregations you have, the slower it would become to process, but performance of queries as well. As the files would get bigger and bigger, the file cache of operating system would be less and less capable of dealing with such bigger files. So again, as a rule of thumb, number of aggregations should not exceed a few hundreds. Now, to continue, what would be the typical cycle that you would do in building aggregation? Use the aggregation design wizard. Put something like 20-30 performance gain. Then enable query log, with something like each 10th query should be logged in. And after a while, after you use the system for a while, use the usage-based optimization wizard and specify a larger performance gain. Usage-based optimization wizard is derived from the aggregation derived algorithm. However, it gives more weight to the queries that you mostly use. So you should periodically after that utilize usage-based optimization wizard to refine the aggregation. And even though it's not on my slide, I'll mention there is a sample tool that we have developed in here, which is actually sample code. It's not a tool that you can utilize to manually manage the aggregation by still abiding by the rules I set in the previous slides, by the rule of thumb. You can manage certain aggregation that aggregation design wizard might have skipped. You can design those manually to add the aggregations that you are mostly interested in. And this sample code would be included in the AS2005 SP2 samples that will deliver with Service Pack 2. Now we are going to move to the processing section to see what are the performance gain that we can get for the processing operation. To understand that, a little bit of the processing architecture. When you try to process an object, even though it's a single object, inside there are multiple tasks that comprise that operation. It's like a mini SSIS package that happens inside. We have a mini execution SSIS-like. Basically, an operation includes creating multiple jobs that have dependencies among them, and those jobs could create their own other jobs, which are child jobs of them. And performance would therefore depend upon how you tune the parallelism of the tasks that the system should be allowed to use for processing those internal jobs. For example, a dimension processing job includes 4 types of tasks. It includes building the stores for the attributes, and then optimizing, so indexing and decoding, and also building the hierarchy stores. And I'll illustrate this in the next picture. The first task that needs to happen in the list of dependency, the big egg on the left side, is building the attribute store. So first thing we need to do is to process the attribute, assign surrogate keys for each and every attribute value. Then we build a hierarchy store. So for each hierarchy, we need to associate parents and childs in the hierarchies. And at the same time, we need to build indexes for the dimensions such that they are such that the queries to the dimensions happen very fast. Now, building the hierarchies can happen only after the attributes stores have been built, while the indexes, which are the decoding stores and the bitmap indexes, can happen only after building attribute stores happen as well, but they can happen in parallel with the hierarchy stores. Within each big egg, there are some smaller eggs that you see. And for example, the hierarchy stores, the 6 small eggs, each hierarchy can be built in parallel. They do not have dependency among each other. However, inside the attribute store, you see something that looks like a tree-like structure. And that is the dependency graph of processing the attributes. Not all the attributes can be processed in parallel, but rather by topologically sorting them. And this is illustrated in the next slide, where we can see that the state attribute processing can happen only after the country attribute processing happens, because we need to refer to the surrogate keys of the country. And it's obvious here that the bottleneck is, in this example, the customer attribute, because it would require everything else to be processed. And also, it would make a request to look up the surrogate keys that we assign in processing for all the direct related attributes that it has to. So now moving to partition job, we can identify as well some concurrent tasks that happen. For example, for processing factual data, there are 3 concurrent threads that we utilize. One, we send the request to SQL Server to get the data and start reading it. In parallel, in another thread, synchronized with this, we start consuming the rows that come from SQL Server and look them up into the dimension store. This is why processing of partition can happen only after processing of dimension. And the last thread, which operates asynchronously, would write out from time to time the processing buffer to disk when full. Similarly, we process aggregation and bitmap indexes. However, the aggregation and bitmap indexes need to come only after processing of factual data. And for optimizing your performance, we offer a large variety of processing options. I'm not going in detail over them, but they would help you tune performance, and that I would explain a little bit. But before, let's take a look to, I'll skip the demo, and let's take a look, because we are a little bit behind the time. So let's take a look at what the best practices are for processing. And one is to use the automation to control in a script that you would generate, to control how you want the parallelism and memory consumption, and don't just process the whole database. For example, you might want to split processing of data versus processing of indexes, such that you would better throttle the memory consumption. In dimension processing, as TK says, use attribute relationship. Again, it's very important, because remember the picture with the eggs that looks like a tree? The less attribute relationships you have, the more attributes would be directly related to the key. So the bigger the bottleneck and memory consumption. The more attribute relationship you are able to define, the easier it becomes for us to process the dimension key. I mentioned splitting processing of data versus processing of indexes in order to throttle memory. And just the last advice, if you can avoid .NET data sources, use native data sources. It's an order of magnitude faster for processing your data. It's a good advice. Going to optimizing MDX. Well, MDX optimization is a tough nut to crack. It's really hard, and that's not to scare you away or anything. It's just a way to stress that it's a difficult task in itself. Why? First of all, you'd have to utilize a lot of tools to tune the performance. You have to utilize the profiler, to utilize the performance counters, to figure out what is going on inside. And then utilize that knowledge to tune your MDX, because there are multiple ways to write the MDX in order to achieve the same results. And in order to help you do this, there are lots of best practices how to do that. If you think that your system is going to be utilized in a multi-user fashion, then the task becomes even tougher, because you'll need to simulate the load over multiple users, like 1 user, 2 user, 4, 10, and so on, and compute the appropriate hardware that you'll need for your system. Basically, compute how many servers you would need for distributing your database and utilizing load balancing. Out of the whole do's and don'ts, I picked up 3 most important, and it's a subjective ordered list. I picked the 3 most important things that I considered, that I've seen in my experience, to recommend. The first one is non-empty behavior. Non-empty behavior specifies a list of measures that a calculated measure is able to derive its non-empty behavior from. For example, if we have a calculation that it's a profit, which is sales minus cost, we could make the observation that the profit behaves with respect to nulls the same way as as sales behave to nulls. For example, when sales is null, profit typically is null, and when profit is null, sales is null. So, in this condition, specifying that profit behaves as a base measure, as a storage engine measure, greatly improves the performance of non-empty queries, and many client tools send non-empty queries, including Excel, ProClarity. Now, how do we utilize this information inside the storage engine? Well, when we specify that the profit has the same non-empty behavior as sales, for the non-empty part of the query, we are utilizing sales in lieu of profit, and therefore we're starting to evaluate just the fact data instead of looping cell by cell over it. You have to, it's just a query hint, and specifying incorrect non-empty behavior, something that is not true, sure will make your query work fast, but it will also lead to incorrect results. So use it with care. But definitely, this is the first most important optimization technique. The second optimization technique is use the auto-exist that's built into the product. By this I mean when you cross-join attribute members from different attributes within the same dimension, only the combinations that it says to exist with each other are returned. As an example, cross-joining Seattle with all of the states would just lead to Seattle, Washington, just because all the other states do not exist to Seattle. And in AS2000, such a query wouldn't have been possible because it would give to all possible combinations. So somebody would have to use filters. So many people still use a filter by member properties instead of simply cross-joining. And here's an example. It's a big performance gain utilizing AutoExist instead of writing custom filters. And the last performance optimization that I want to recommend is to use scopes instead of dynamic conditions. A scope is, I'm not going to getting into details of what scope is and what the syntax is. You can get this from books online. But the big differences between the two statements that I have on top, that I have in the code snippet below, is that utilizing scope instead of if is kind of like the difference between compiled code and interpreted code. The scope kind of compiles that information at parsing time, and then it goes through much faster code paths instead of evaluating the condition over and over again. So please utilize scope whenever you can instead of dynamic conditions. It's not always possible, but whenever you can, utilize that. And at the end, I do have here a list of best practices. It's not, it looks like a laundry list, which probably this is what it is. Not going therefore over each and every of them. Just wanted that you would have them if you download the slides. And you can find many more things at SQLjunkies.com. There is a web blog of Moshe Pasumansky, as well as lots of other white papers on SQL Server Analysis Services.com. And with this, the section is concluded, and I'm going to turn over to TK for the conclusions of this talk.
Okay, thanks, Christian. So yeah, and just to conclude here, we've gone through various aspects of analysis services, cube design, partitioning, aggregations, calculation performance, and kind of pointed out some of the core principles for design and offered some best practices here. Now, a lot of the concepts are actually not new if you're an AS2000 user, but some of the new principles like attribute relationships and some of the new design alternatives like role-playing dimensions, many-to-many dimensions, are things that you have to kind of get used to and play with them a little bit to understand the performance implications. So with that, I'd like to conclude this talk. I have been monitoring the questions and answering them as they come, but if you have any more questions, then now would be a good time to ask. At this point, I can hand it over to Janet.
Excellent. Well, thanks, TK. And I'm just going to remind everybody that if you have questions for TK, or you can go ahead and submit those now, so we'll get to them in just a moment here. So we do record all of our sessions. I'd like to let you know that if you'd like to see any of our previously recorded webcasts, as well as anything that's coming up, you can go to Microsoft.com/webcast, and they're all posted right there. If you have content ideas, anything you want to see us do differently, go ahead. We have yet another link there, and we'd love to hear from our audience. And if you have any additional questions, like I said, for TK or Christian, go ahead, submit them now. We're going to get to those in just a moment. But I do want to let you know today's webcast was presented using the Microsoft Office iMeeting technology. To get a free 14-day trial, just go to Microsoft.com/present-live. I'm going to post up a survey here. I just want to remind you all that your feedback is very valuable, so if you could take a moment to fill out the survey before you log out, we do appreciate that. And I'm not seeing any additional questions coming in. TK, Christian, any additional last words you want to go through?
No, that's it.
Excellent. Well, we can remain online for just the next few minutes, and if any additional questions do come in, we can answer those via the Q&A text window. So still feel free to ask any questions that you might have. Also remind you that You can watch your inbox tomorrow. I'll have an email with information about viewing this particular webcast on demand. You'll be able to download it as a Windows Media file. And that email is also going to include a link to the downloadable PowerPoint of today's webcast as well. So with that, I'm just going to extend a special thanks to both TK and Christian. Great information. And that concludes today's MSDN Live meeting. So thank you, everyone, for joining.